Actually, can he hear you speak?
Sorry?
Can he hear you speak?
Yes, he can.
Okay, but
He can hear you as well.
He can hear you too.
Tell her it was lovely singing.
Okay, it was lovely singing.
And she's currently on a live stream.
Okay. I can't sit here. You're gonna have to give me 2 seconds to move.
Yeah, I was gonna say if that music's gonna be in the background, that might be a little annoying.
It smells like rotten eggs here.
Oh gosh.
Okay.
Right. All right.
Right.
Okay, so I was, as I was saying, it explains a little from the AS sessions that you've already done it once, so you're obviously significantly more comfortable than the guy doing it for the first time. But, all right, so obviously I have a fair idea of this paper now, having just done an individual live stream of it, but let's talk about it then. So this is more going to be about the stuff that you personally want to talk about. If we want to talk about generalities about things, then there is now a video available for that on YouTube, or there will be once it's rendered. But what would you like to talk about for this? So where would you like to start?
So since I haven't looked at this before this time.
So you haven't looked at this paper yet?
No, I have looked at this paper, but most of it is new to me because
the material itself is new.
Yeah,
yes.
I haven't looked at A2 before. So one thing that I really have trouble with is number 2 when it started on gases specifically, because I'm not specifically good with moles and stuff like that. I haven't done particularly much with that.
So do you have lessons at all in this school?
No.
Right. Okay. So do you have a textbook of some description?
I'm busy getting one. That we weren't given one, so I'm trying to find a good one.
Yeah. Because, I mean, while jumping straight into papers is all well and good, if you've never seen a topic like ideal gases before, you do need to learn some of the stuff about them before you just jump right in.
Exactly why I'm getting the textbook. I've found that is something that really needs to be done.
Yeah, that is definitely the case. All right, so in that case, let's talk about ideal gases. So, let's run through this question from start to end, essentially, then. It is one of the trickier ones on the paper, in all fairness.
Okay.
What is meant by an ideal gas? So this is a good place for us to lead in. I'm pretty sure we actually discussed this in the AS physics paper. So this is essentially an extension rather than a brand new thing to you. So first off, what is an ideal gas? Talk to me about that. What are your conditions on it?
Wait, where's my paper?
Okay, don't reach for your paper and try and read it off. Just talk to me. Tell me from
Um,
your head, as it were.
so an ideal gas is where the elasticity, when a particle collides with another particle, it's a perfectly elastic exchange of energy. And from what I know, I think that's,
Okay.
yeah.
So the key points for that side of things are the particles are so small as to essentially take up no volume. They are
Okay.
non-interacting except by collisions, and the collisions are elastic.
Okay.
Those are your conditions. Now, that is actually the kinetic model of gases. That's what that is. Okay.
Yep.
Now, the kinetic model of gases, at its fundamental, is in fact an ideal gas. However, it is interesting, and this is the sort of thing where marked schemes come in very handy. So, at AS, they asked you to describe the kinetic model of gases, and it was what we were just talking about. However, apparently at A2, when they say what is meant by an ideal gas, what they are actually really asking is for the ideal gas equation to be explained, apparently.
Okay.
The only reason we know this is by looking at the mark scheme. So in their mark scheme, they are looking for you to say it obeys the equation PV equals nRT. That's what they want you to say, and then they want you to explain this.
Okay.
I'm not completely certain what they're talking about, but yeah. So where P is pressure, V is volume, T is temperature. And then they've got a slightly curious line here. All values of P and V. So yeah, that first part is worth saying, for any pressure, any volume. And T fixed mass N is constant.
Yep.
That's a slightly weird thing because that's not actually true. But yeah. So the key point is to say that it obeys the ideal gas equation, and this is what all the stuff is. So P is pressure, V is volume, T is temperature. Those ones are nice and easy. What are N and R in this equation?
I have no clue.
Right. So that would be worth talking about then. So
yeah.
I'm assuming you were already happy with PV and T being pressure, volume, and temperature.
Yes.
All right, they're the first. Those ones are always nice and easy because they're the first letters. It kind of makes sense.
Yep.
So R we will start with is, I can't remember its exact name, but it is the gas constant.
Okay.
It is just a number. It's 8.3 roughly. It's one of the few constants where it's genuinely like a really normal sounding number. It's like 8.3. It's not sort of times 10 to the 15 or something like that. It's about 8.3. It's just a number. It's a constant. It's in your data book, or rather, actually, in this case, it's at the front of the paper, isn't it?
Yeah, it is.
So flick up here, we can find R is 8.31 joules per Kelvin per mole, molar gas constant. More specifically, it is actually, so you will notice that this is why it comes out as such a nice number. It's actually R equals K N A.
Okay.
And the 10 to the 23 and the 10 to the minus 23 cancel out, which is why it's such a nice number. But yeah, so that is what R is. And it's just a constant. It's, where are we? 2. There we go. Yeah, so R is just a constant. The last one is N. So what is N? What does it stand for?
It would stand for
Any clue based on the name
moles.
of... Yes. So N is our number of moles. Now,
Yep.
you've already said to me that you're not terribly comfortable with moles, so we're going to talk about them for a bit.
Yep.
So what is a mole? If I say I have a mole of something, what do I mean?
I believe it's like a quantity of particles, or like a weight of particles, I guess.
Yeah, so a mole is a number. It is a way of counting things. So essentially, we use moles when we want to essentially count things, but when we have so many of them that counting them regularly becomes inconvenient. And it works off of Avogadro's number, which we just looked at up here. Avogadro's number is 6.022 times 10 to the 23.
Yep.
So essentially, I mean, up here they've given it units of, up there they've given it units of per mole. Realistically, Avogadro's number is actually just a number. It doesn't really have units, right?
Okay. Yep.
A mole is where we have that number of particles. So if we have 1 mole of carbon atoms, we have 6.022 times 10 to the 23 carbon atoms. So in this case, yeah, it is just how many particles of our ideal gas do we have, and then we're counting them in 6.022 times 10 to the 23s. It's obviously a fairly large number to group things into, but that's what we're doing for the sake of actually having reasonable numbers of things. The reason that we say that we use R is because you can also use this in the form capital N KT, where again, K is just a number, but this time capital N is the actual number of particles rather than the number of moles. And so the conversion is just whether we are counting particles or moles. So capital N will be a really, really big number of the order 10 to the 23, whereas N will be a normal size number because it's number of moles. So in terms of the physics side of things, that's what we're dealing with. Moles is just a way of counting things. How people decided on the specific number 6.022 times 10 to the 23 is more a discussion for chemistry, but it's based on 12 grams of carbon-12, essentially. For now, though, that's what we're dealing with. And for gases, we're just looking at it as a way of counting. Okay, so now we deal with this side of things. So we have 2 cylinders, and they are obeying our equation PV equals nRT. So at first we have cylinder A with we have a certain volume, a certain pressure, and a certain temperature. If we've got P, V, and T, and obviously we know R because that's just a number, we can work out our number of moles. Yeah. So we can rearrange, we can say N equals PV over RT, and we'll get that answer out. I'm assuming that you were fairly happy with doing that, right? Yeah. Because, I mean, this is one of those things where whether you understand it or not, you can still put the numbers into the equation. So that one would have been fine. And, you know, disappointingly, they knew it was fine. It's 1 mark. Continuing on, this is the more tricky bit. Cylinder, I apologize, by the way. The reason this is already pre-annotated is because, as I said, I've just sort of streamed a go through. Did you see the... Wait, what was it that I streamed? Was it? Yes, it was physics, wasn't it? Yeah. So did you see the stream I did of the physics paper?
The earlier one.
Yeah, the one from last week.
Yeah.
How was that? Was that one all right?
Yes, it was really good.
Cool. All right. So this time around, we're saying, all right, now we're going to open our tab. I'm tempted to try and zoom out a bit, but I don't know how well you'll be able to see that bit. So now we're going to open our tab. Now, I mentioned this in the stream. So when they say connected by a tube of negligible volume, essentially what they're doing by this is they're creating this imaginary setup where we can connect and unconnect cylinder A and cylinder B without changing anything else. And so what we're saying is now that we open our tap, they are now essentially one big volume that's stuck together. Yeah?
Yeah.
So essentially what we've done is stuck them together with no boundary, suddenly and instantaneously by magic.
Yeah.
That's what our kind of imaginary volumeless tube does. After we have opened our tap, we have a new pressure of 3.9 times 10 to the 5 pascals over here.
Yeah.
So determine the final temperature of the gas. So again, PV equals nRT. We've been given a volume of cylinder B. We knew a volume of cylinder A. So our total volume is going to be the sum of those two. That makes sense. That seems fine. We have been given a new pressure. So we've got a new volume. We've got a new pressure. We are looking for a new temperature. And lastly, we have our new number of moles, because we had 0.2 moles in B, and we've already worked out that we had 0.34 moles in A.
Yeah.
So we have P, V, and N. R is just a number, and so that will allow us to work out T equals PV over NR. Seems okay, right?
Yeah.
A little bit more involved, because we are this time, we're doing a little bit more than just plugging numbers into the equation. We have to work out what those numbers are logically, but it makes a reasonable amount of sense. Question C is conceptually probably one of the hardest questions on this paper. So what we're going to talk through is what's actually gone on here and why does it make sense. So what they want you to say is, why has our temperature changed? So if we look, before, our temperature was 300 Kelvin in cylinder A. Yeah, over here. And afterwards, what we will discover from the mark scheme is our temperature is now actually 360 Kelvin.
Yeah.
Well, that's a lot higher. Our temperature has gone up significantly in cylinder A. And what we're asking is, why is this? So what we want to say is, well, most notably of all, actually, what's happened here is our pressure has gone from 3.4 to 3.9 kilopascals. I can't draw points on this with this software because it's so laggy, but we've already discovered this. You'll remember that from last time. So our pressure has gone up, right? That's the important point here. So if we, for a second, look at the point of view of the gas in cylinder A, right? In cylinder A, we had some gas that was at 3.4, and it's been compressed to a new pressure of 3.9. Yep.
Yep.
So that gas has been squished, essentially, right? We've gone from a pressure of 3.4 to 3.9. We've compressed that gas by allowing the higher pressure gas of cylinder B in. And in doing so, we have done work on it. Okay?
Yeah.
So we've compressed that gas, we've done work. Now, up here, I was trying to underline it at the time, but I kind of scribbled through it instead. We've said no thermal energy enters, or more importantly, leaves the gas. So if no energy is leaving, but we're doing work on the gas to compress it, then that energy is going to be left in there as new thermal energy. If we're leaving internal energy in there, the temperature has to go up because the temperature is a measure of internal energy.
Yeah.
Does that make sense?
Yes.
So that's what we were going for there. Some of the gas has moved from cylinder B, which had a higher pressure, to cylinder A. So it's compressed it's compressed the gas that was in cylinder A to start with and done work on it. And in doing so, it's raised its temperature.
Yeah.
That's what we were looking at here. It's quite a nice examination of what's going on here. It's quite a nice overview of the various points and kind of getting you to do some of the maths with the ideal gas equation. Has all of this made reasonable sense in terms of what we're doing here? Are you happy to carry on, or are there some other questions that you would like to ask about ideal gases in general that weren't directly covered by this question?
No. If I come up with any, I'll ask them during the masterclass. But right now, I can't think of
Well,
any.
this is the masterclass, but
Yeah. During in
during the rest of
continuation.
it, yes.
Yeah.
All right. So
Yeah.
let's carry on then. So where would you like to go next?
On the question
so
C.
Bearing in mind, I think,
Mhm.
unless you've been told otherwise, the plan is that we are going on with this until 6 o'clock.
Yeah.
Yep. So
Mhm.
we've spent a solid sort of 20-25 minutes on that. So we're definitely not going to go through most of the questions on this.
Yeah.
So question 6, did you say?
5.
5.
Yeah.
Right. No, that's question 5. Okay, so 5 part A, define the Tesla. That's kind of,
Yeah.
I mean, I'm assuming you don't particularly want to talk about that. That's just a definition, right?
That's just a definition.
So question 5 is actually quite a short question.
Yeah.
Oh, is it? No.
It's got 2 pages to it, but
Which one? Oh, it caught me off guard. Question 5, because
okay.
when I was doing the thing, because it was quite so short. But that's partly because question 6 is pretty much on the same topic in a lot of ways. So this is all about coils and electromagnetic induction. So the first part is coils as an electromagnet, and we've just got this equation, B equals mu naught Ni. The one thing that I did want to make a point before we start talking about it is this N is a constant equal to blah, right? That is a truly bizarre thing to say. So what is N, realistically speaking here? Do you know?
No, it's
Right.
the
Okay,
thickness
so
of the wire.
no. So
No.
this is really bizarre. I don't know why they're saying that, because it's such a simple thing. So this equation, let's talk about it. This is the equation for the magnetic field that is going through the middle, right?
Okay.
So we have a magnetic field B going through the middle of the wire that is generated by our coil. Specifically, you know, this coil over here. It's generating a magnetic field in the middle, which is a constant field of strength B. And this is just an equation for how strong is the field in the middle of a coil of wire, right?
Yeah.
Because when you have current going through a coil, you generate a magnetic field. Mu naught is the permeability of free space. And that's just a constant. Let's find it. It's 4 pi times 10 to the minus 7. It's a weirdly nice constant. I'm on the wrong page. It's one of the few that you can really easily remember. Yeah. So mu naught, 4 pi times 10 to the minus 7. Aren't you dead impressed that I knew that? 4 pi times 10 to the minus 7. It's just a number, right? That's all there is to it. It's just one that shows up in these things. I, the current through the wire, right? And that one makes a lot of sense. The more current you put through something, the stronger a magnetic field you're going to get out.
Yeah.
Seems nice? Yeah.
Yeah.
Cool. Last one is, and this equally makes sense, right? The number of turns on the coil.
Mm-hmm.
If you've got, one loop of wire, you're not going to get much of a magnetic field out of it. If you've got lots and lots and lots of loops, it's going to go better. And
Yep.
that's all this is. However, it's saying that actually, more to the point, it matters how many turns you have per unit length, right?
Yeah.
Because it doesn't matter, if we've got a meter long set of wire with 20 turns on it, and then we
Mm-hmm.
stick another meter with another 20 turns on it, that's not going to change how strong the field is in that first meter. It's just going to make
Mm-hmm.
it a meter longer.
Yeah.
So N is our number of turns per unit length, which is why it's got these units of per meter, right? It's just
Mm-hmm.
counting per meter. So in this case, when we say 1.5 times 10 to the 3, that is a slightly bizarre way of writing things. What we're really saying here is we have 1,500 turns per meter. We have 1,500 loops of wire crammed into a meter of coil. Does that make a bit more sense?
Yeah.
All right, so now we have our equation. It makes a lot more sense given that we know what we're talking about. And so, yeah, we're just putting numbers in at this point, right?
Yeah.
We've been given I was 3.5 amps. We've been given N is 1.5 times 10 to the 3. And so, yeah, B equals mu naught Ni, that's nice and easy. To be honest, I think 2 marks is quite generous for putting things directly in without even rearranging it. That's being very kind from them.
Yep.
Now, this second part is a bit weirder, but it will make a lot more sense in a moment. So, flux linkage. Where have we heard the term flux before? Well, we've heard it up here.
Up here?
Right?
Yeah.
Flux density. So,
Mm-hmm.
we measure magnetic field strength in what we call flux density. And
Yeah.
what we mean by this is if we have a magnetic field,
Mm-hmm.
We have a magnetic field B with our magnetic field lines. And if you imagine putting an area in, the flux density is the amount of magnetic flux per unit area.
Yeah.
Right? And essentially what that means is we're saying, okay, how many of these field lines are going through our unit area?
Yeah.
Does that make sense? And
Yes.
so that's why if we want to draw a stronger field, for instance, we would draw more dense lines within the same area.
Yeah.
Okay. The flux linkage is just taking away that per unit area. And it's saying, if we have a given amount of area, how much flux is going through it?
Mm-hmm.
And so that is just very simply the flux per unit area times the area.
Mm.
Does that make sense?
Yeah.
And we call this capital phi, the flux linkage. So phi equals BA. And this is just a kind of circular definition, right? The flux linkage is the flux density times the area, but more to the point, we're saying actually the flux density, B, is the flux linkage divided by the area that is being linked over. It's called linkage because you describe it as linking that area. It's a slightly odd terminology, but yeah, essentially it's asking us for this area A, how
Mm-hmm.
many lines are going through it? That's essentially what we're talking here. Does that make sense?
Mm-hmm.
All right. So Faraday's law of electromagnetic induction then is all about this flux linkage. And it says the electromagnetic force, the voltage that you induce by doing electromagnetic induction, is proportional to the rate of change of phi, of the flux linkage.
Yeah.
Okay. So down here, I said that. So have you done much maths? Presumably so.
Yeah.
Yeah. So you're happy with differentiation. So realistically,
Oh, yeah.
this is actually in terms of d by dt of phi.
Mm-hmm.
However, in the physics A level, essentially they aren't allowed to assume that you've done maths. It has to be possible to take physics without doing maths. And so in
Okay.
reality, what we deal with is average EMFs, and we deal with delta phi over delta t, i.e. a whole time integral, a whole time interval even. So Faraday's law of electromagnetic induction is EMF is proportional to the rate of change of magnetic flux linkage. And so in this case, we say if our current is reversed in direction, our flux linkage is going to go backwards. And so delta phi is going to be 2 times whatever our flux linkage started out as. Does that make sense?
Yeah.
So we've changed by double that. We've been given a time interval, and so we're just going to divide them, and that's going to give us our answer.
Okay.
All right.
Yeah. Yeah.
So their statement in the mark scheme is essentially what you want to learn as far as part 1 goes. They've got a statement in the mark scheme. That's what they like to say. And yeah, for a lot of these things, for when you're asked to define something or state a law, you just need to know what wording this particular exam board likes. That's what they're all about, unfortunately.
Okay.
But that's just kind of how it is. So electromagnetic induction.
Okay.
It's all about saying we are moving something through. In this case, this is about we have some stationary coil of wire, and we're changing the magnetic field by changing the flux linkage. What I'm briefly going to do, since you're obviously not too comfortable with the topic, is I'm briefly going to talk to you about the other thing and the more common way that we see this, which is if we have a wire and we move it through a magnetic field.
Yeah.
Okay. And essentially, if we have a magnetic field B that's going, let's say, into the page. So, by the way, the other thing, are you familiar with this way of drawing a magnetic field? Have you come across this before? Right. So, this is a useful thing to come across. So, essentially, usually, this isn't any field, actually, right? With a field, you draw it as arrows.
Yeah.
This is arrows in 3 dimensions. And essentially, this is imagining that we have an actual physical, like arrow, as in you would shoot out of a bow, and it's whether it's coming away from you or towards you. So if the field is going into the page, we draw it like this, as a circle with an X through it. And this is as in, if you are looking down an arrow, this is looking at the tail feathers.
Okay.
Whereas the other one is, if you're looking at an arrow coming towards you, you can imagine that would have a cone on the end, and you've got the point of the cone and then the circle around it being the base of the cone.
Yeah.
So yeah, that's how you draw a field going into or out of the page, as opposed to, arrows which are going along the page.
Yeah.
And what we would do in this case is we would move our wire through our magnetic field. And what this would give us is once you've moved your wire to say here, you have swept out this area A. Does that make sense?
Yeah.
And so what you've actually done is you've changed your flux linkage by an area BA over the time that it took you to give to do that motion.
Okay.
Does that kind of
Yeah.
make sense?
Yeah.
And so that is your Faraday's law. You've done a change in flux linkage of BA over a time t that it took you to sweep it out. And so this is what's happening when you have, you know, a wire moving through a magnetic field to generate electricity.
Okay.
And a lot of the time, what you will have is a whole coil of wire doing this. But yeah, that is a common and slightly odd way of seeing these things. And so it's just worth talking about, I thought.
Okay.
All right, so where next?
I'd like to go to the next question because it's kind of similar to it.
Yes, it's very much the same point. So this one now is about transformers. So the first part, why is the iron core laminated and what is meant by an ideal transformer? Are you happy with that?
Kind of.
Okay.
This is like new to me, so it's
all right. So in that case, we'll talk about it regardless. So we'll talk about it anyway, but these are just things that you need to know. Okay? So why is the iron core laminated? It is to reduce power loss by eliminating or reducing eddy currents. Now, eddy currents are the reverse of what we were talking about, or well, not even the reverse. They are what we were talking about in the last question. So we have this big, thick iron core, which is made of metal, full of electrons. It can carry a current. And we have this changing magnetic field in a transformer, right? That's how it transfers energy from one coil to the next. And so with this changing magnetic field, in our big metal iron core, we actually induce currents. And they're called eddy currents. And what you get is you get lots of little currents going round in circles.
Okay.
You get lots of little currents going round in circles all around the transformer, or you would. And because you've got a current moving in a metal, that metal has a resistance and it will dissipate heat. Makes sense? And that is where basically all of your energy loss from a transformer comes from. Now, the bigger a distance you can make it over, right? You remember that when we're doing electromagnetic induction, we're looking at flux linkage. And the really important bit here is our area. Now, the smaller we make our area, the smaller our current is going to be and the less power we're going to dissipate. So rather than having lots of big, powerful eddy currents, which are dissipating loads of heat, what we want is to make them as small and negligible as possible. And to do that, we laminate our iron core. And what that actually means in practice is that our iron core is split up into lots of electrically isolated layers. So we've got lots and lots of thin layers of iron with some kind of electrical insulator in between them that stops an eddy current flowing between layers. And so it confines these currents to these very thin, small layers, and therefore to very small areas and very small currents. And so we dissipate less power. Does that all make a bit of sense?
Yeah.
Good. Okay. What is meant by an ideal transformer? Essentially, an ideal transformer is we imagine that none of this is going on. That's what it is. So we say it dissipates zero energy. Essentially, we pretend that all of the magnetic field is going from one coil to the other and everything is perfect. and all of the energy from one current is going into all of the energy from the other. And that's it. So, no power lost, input power equals output power, something like that.
Yeah.
And yeah, essentially laminating the core is just our attempt to get as close to an ideal transformer as possible. When you deal with transformers at this level, when you do maths on them, we are always assuming, unless you're told otherwise and told how to do it, which they might in a question, but it's unusual. We are always assuming that we have an ideal transformer. Okay?
Yep.
All right. Now this one, our ideal transformer has 300 turns on the first coil, 8,100 on the secondary. And we have an RMS input voltage. Calculate the peak voltage across the output resistor. So essentially what we're saying is calculate the maximum voltage coming out. So there are two parts to this. The first one is we need to know, what does this root mean square mean? So do you know anything about that?
No.
All right, so root mean square is a way of averaging things out, and it's just different to the regular mean. So the arithmetic mean means you add them all up and divide by the number of them, right?
Okay.
The root mean square means you square them all, then you add them all up, divide by the number of them, and then square root that at the end. It's a slightly curious thing to do, but it's a very good way of averaging out, what do you call it? Like repetitive things. So in this case, it's a very good way of averaging out sinusoids, and it's very useful for power and stuff. The key thing that you need to know about root mean squares is this. So for a sinusoidal curve, so a sine, a cos, anything like that that does this, the root mean square is equal to your maximum value that you are reaching, assuming that, of course, this is 0. It's equal to your amplitude divided by root 2.
Okay.
All right?
Yep.
That is, and essentially, that's all you really need to know about the root mean square. That it's a useful way of averaging out inputs for things where they're, varying back and forth between positive and negative. But mainly, it's max over root 2.
Okay.
So the second point then is our standard transformer thing, where we're saying the voltages are proportional in exactly the same way that the number of turns are. So we've gone from 300 to 8,100. So we have times 27. That's what we're doing to the voltage. And so if we've got RMS over here, we're going to do 9 times 27, which is lots.
Yeah.
What is 9 times 27? I should know that. Hang on. That's 81 times 3, which is 243. Is that really right?
Okay.
Curious. Okay, so we get 243 as our new RMS voltage, right? So we've converted our RMS into our RMS out. Now we need to turn that into a peak voltage. So turning the other one around, we can say that our maximum is going to be RMS times square root of 2.
Okay.
And unless I'm very much mistaken, that should give us 340.
Yeah.
Excellent, because that was the answer. Cool. So there we go. Yeah, that's root mean squares essentially. So the real meat of this question was all about root mean squares, and yeah, no, it was this one that caught me off guard actually with how short it was, because it was literally just this. It was like two definitions of a transformer and then a 2-mark maths question. That was the whole question. I was like, wait, where did the rest of the question go? But that was it.
Mhm.
Yeah, so that's about it as far as transformers go. Just lastly, we're going to talk about how do transformers work? How does the energy get from one side to the other?
Okay.
I'm asking you.
Oh, okay. I believe the ions go through I'd expect that it goes through the input of the transformer and it goes into the secondary coil.
Okay, yeah,
I haven't.
but
Yeah,
how does our energy, how does our electric current get from one
yeah.
coil to the other?
Through the metal plates. It transfers during the coils. It transfers to the plate of the big thing.
Okay, so this is important to note. So
Yeah.
with a transformer, there is no flow of actual electric current, right? Because if we had
Okay.
a genuine electric current, then we couldn't change the voltage and current, and that's
Okay.
what this is all about, right? Is changing the voltage.
Mhm.
So the way a transformer works is it's on AC, alternating current, right? And what
Yeah.
that means is that our current is on a sinusoid. Most importantly, it's going from positive to negative.
Okay.
And what that means is it's changing direction. Yeah?
Mhm.
So we've talked earlier in the above question about inducing a magnetic field in a coil like this.
Yeah.
Yeah? Now, if I were to turn the current in the coil to go the opposite direction, what would happen to the magnetic field B that we've drawn?
It's a reverse.
Yeah. And so that's what happens in our transformer. So our input is AC. That's what this squiggle by here means. It's an AC generator.
Mhm.
So our current is going backwards and forwards. Now,
Okay.
because we've got this big iron core, our iron core is easily magnetizable. And so what happens is our magnetic field goes through our iron core.
Okay.
And our current induces a magnetic field in the iron core as it switches. That's the key point. So our current induces a magnetic field in the iron core. But when our current is going in one direction, our magnetic field is pointing this way around. Whereas but then it's going to switch and it's going to point in the other direction.
Okay.
Now this is happening all the way through the iron core. And so what you get happening is exactly what we talked about towards the end of question 5, where we have a magnetic field going through our secondary coil, which is constantly reversing direction.
Mhm.
Now, we have phi equals BA. Obviously, the area on our coil is not changing because nothing is physically changing here. But
Yeah.
our flux linkage, our magnetic field strength B, is actually acting on a sinusoid, right? Because it's proportional to our input current.
Mhm.
And so what's going on here is our B is constantly going like this. Our
Yeah.
magnetic flux linkage is changing. And so Faraday's law tells us that's going to induce a new voltage.
Yeah.
And so what happens is, because our input coil, our first coil, is constantly causing this changing magnetic field, that constantly changing magnetic field is inducing a new current in our output coil.
Mm-hmm.
And so it's these two stages of electromagnetic induction. That's how the energy is getting from one coil to the other.
Yep.
All right?
Yeah.
Cool. Okay, so that's how transformers work, and that's important to know.
Okay.
So I know I labored the point a bit. I know I was a bit, over the top and oversimplistic, but hopefully that was a good start, given that you hadn't come across them before.
Mm-hmm.
So we have 5 minutes left. Where would you like to go for one last time?
So I'd prefer to go down to part 7, but since we don't have that much time, just the final 2 questions of it, I think it was.
Okay, so yeah, part 7 is the photovoltaic effect.
Yeah.
So what this is all about, essentially, the core idea of the photovoltaic effect is we have some surface of metal with some electrons in.
Mm-hmm.
And what we're essentially saying is, if we want to get these electrons out of our surface, we need some energy phi. Okay?
Yep.
Now, an electron can only gain energy from light by taking in a single photon. Okay?
Mm-hmm.
So if we take in a single photon, we are going to get that photon's amount of energy. And a photon has energy E equals HF.
Yeah.
So the energy that an electron has after it comes out is going to be HF, the energy that it gained from that photon, minus phi. Now, if HF isn't as big as phi, it doesn't have the energy that it needs to get out, and so it's not going to. If HF is greater than or equal to phi, then it will have enough energy to get out, and it will have HF minus phi, which is now positive, kinetic energy left over to then go and fly off and do whatever a free electron does, go to parties, whatever.
Yep.
That seems okay, right, as a base idea.
Yeah.
So the threshold frequency is just whatever frequency is needed for HF to reach phi, our amount of energy that we need to get out.
Mm-hmm.
So HF naught, our threshold frequency, equals phi.
Mm-hmm.
And then any frequency above that threshold frequency. And so at the threshold frequency, our electrons will in fact escape with 0 kinetic energy.
Yeah.
At anything above that, they will then have whatever's left as kinetic energy to go and fly off. For the last 2 questions then, what we're saying is, so for this one, we're given a set of wavelengths. So we're saying F equals C over lambda. So at 300 nanometers, that's going to be whatever. And at 600 nanometers, it's going to be half that frequency. So if I just have a look for the sake of it, apparently at 300 nanometers, we get 10 to the 16 hertz.
Yep. Mm-hmm.
Now, we have some threshold frequencies up here. Our threshold frequencies are all in 10 to the 14 hertz. And then this last one, we should have calculated to be 1.4 times 10 to the 15. I can't draw points to save my life. This is really annoying. Anyway, so at 600 nanometers, we're going to go to F equals C over lambda.
Okay.
F equals C over our new lambda. And which is going to be, so 600 is going to be 5 times 10 to the 15. Okay?
Yeah.
Right, so each of the metals listed in figure 7.1, which I'm assuming is that. Yeah, so shouldn't they just all emit? We're well above the threshold frequencies here. It seems like a slightly curious sodium and zinc. Why wouldn't we be emitting from platinum? I'm confused here. If it has a threshold frequency of 1.4 times 10 to the 15, and we have a frequency of 10 times 10 to the 15, why does their mark scheme not think that it's... Oh, I see. They're just ignoring sodium because you could have potentially not worked it out. No, they're not. Oh, I don't know. They're slightly bizarre here.
Okay.
I'm confused. What is going on here? I think they've made a mistake here. I think they've made a mistake. Oh, well, right. Either way, yeah. So the important point about that question, regardless of what their mark scheme says, is that it will emit if the threshold frequency is greater than the, it will emit if the frequency of the light is greater than the threshold frequency. That's all that's actually important here. Now, the last part is the interesting point. So this is the difference between intensity and frequency. And a good explanation of this is to look at it in terms of photons. So we're happy that photons are particles of light, right? It's a little bit of light. And a good way to think about this is that you've got lots of little photons with tiny imaginary arms, and they are each carrying an amount of energy, right?
Yeah.
Intensity is the number of photons that are coming in. Frequency is how much energy is each individual photon carrying. Does that make sense?
Yeah.
So when we have electrons coming out of a surface, whether they will escape is dependent on how much energy each electron has, because they can only take energy from one photon.
Okay.
So whether they can escape is dependent on the frequency. That's dependent on how much energy is each photon coming in carrying.
Okay.
However, the rate of emission, how many electrons we are emitting, is dependent on how many photons are coming in, provided that they are able to escape. Does that make sense?
Yeah.
So if none of the photons are able to get an electron out, obviously you're going to have a rate of emission of 0.
Okay.
After that, the rate of emission is dependent on how many photons are coming in, the intensity. And there's this kind of binary if or if not about the frequency. So we have said if we've got the same intensity, then up here at the top, and this is essentially F0. So as we vary our frequency, if we are below F0, then we're not going to emit any electrons because we aren't being able to emit any. We don't have enough energy on each photon. So that's fine. Above F0, we are going to be emitting, but it's going to be at exactly the same value. We're not going to change the rate of emission because we've got light of the same intensity.
Yeah.
The individual electrons that are coming off will have more and more kinetic energy, but there will be the same number of them coming out.
Mm-hmm.
Does that make sense?
Yes.
Good. All right then. We've come to 6 o'clock. We will call it a day there, if that's all right.
Yeah.
I recommend that you go and watch the video. It is a little bit rushed because I'd been asked to make it even faster than before, but otherwise, yeah, hopefully that was all useful to you. I think particularly given that you don't have lessons, it's more useful to focus in on a few questions and go through the topic really properly rather than kind of just focus on answering the question itself, because this is the only real teaching that you're getting. And you do need, much as the whole new model of education and stuff, you do need to be taught something before you can do it. I'm afraid that's kind of how things work. So yeah. All right then. I will presumably see you tomorrow. So yeah, I will see you then. And in the meantime, goodbye.
Goodbye.